Hello everyone, welcome back. Today we're going to do lesson 312. This will be probably a 2-day lesson, so we'll call this day 1. But our focus is going to be on rewriting expressions and determining equivalency. So in yesterday's lesson we talked about equivalency through the eyes of a table, a graph, and then the algebraic proof using the equations at the end. And we talked about why the algebraic proof was probably the most sound, is that because it showed it was equivalent at all points instantaneously, and that, like with the table and the graph, we were not really able to see all of the points at once, right? Whether we were on the table or the graph. So there could have been, some point off towards infinity that was slightly different or something, and all of a sudden they wouldn't be equivalent. So the algebraic proof was the foolproof way of showing that two things were equivalent. So we're going to focus on that today and really hone those skills as far as multiplying and factoring and using some of those algebraic techniques to show that two things are equivalent. Okay. And one of our most common tools that we use is something called an area model. And this is what we call the generic rectangle, or the box, that we see so often whenever we factor or multiply expressions. Okay, so we're going to focus on multiplying and factoring today and kind of go through that and see how I can take an expression that is in factored form and write it in a different form via multiplication. All right, so let's give it a try. So you have to remember that this thing does indeed represent an area model, so it's a big rectangle. All right, and when we see an expression like this, we have one algebraic expression like 3x plus 1 being multiplied by another 2x minus 3. And since these are two separate factors, they're two separate algebraic expressions that are being multiplied, we can use area to help us out with that. All right, so we use this 3x plus 1. Let's say I let 3x plus 1 represent the height of my rectangle. Okay, and then I'm going to let the 2x minus 3 represent the width of my rectangle. All right, so then what I'm going to do is I'm going to find the area of the entire rectangle by multiplying the individual smaller rectangles inside. All right, so watch what I do here. So if I do 3x times 2x, well, I do the 3 times 2 first, which gets me a 6, and then x times x gets me x squared. Okay, so that would be the area of just this upper left-hand box, or this upper left-hand rectangle here, right? Because we did height, we did width, and we multiplied those, and that gave us the area of just this box here. And we could do the same thing over here. If we do 3x times negative 3, we would get negative 9x. So that would be the area of the upper right-hand box. And then we would keep doing this for each subsequent box. So 2x times 1 is just 2x. And then down here we would do negative 3 times 1, which is negative 3. So now I have the area of the four smaller rectangles here. So if I wanted to find the area of the whole thing, I would just have to add these together. So I could say the area of the entire rectangle is 6x squared minus 9x plus 2x minus 3. Right? This would represent the area of the entire box here, and it would be equivalent to this because this also represents the area of the entire box. So these two expressions that I just created, they are in fact equivalent, but I can simplify this a little bit by combining like terms, right? So I could take these two middle terms, the negative 9x and the 2x, and I can combine them because they are like terms. Okay, so I'm going to rewrite that in its simplified form. So I'm going to say 6x squared, and when I combine a negative 9 and a positive 2, I get a negative 7x minus 3. Okay, so this expression and this expression are equivalent because they both represent the area of this entire rectangle. Okay, now in class what we refer to this as, we refer to this as what's called a product or factored form, and this is what we call the sum, right? Because we added. Right? Sum is a fancy math term for adding things, right? So since we added the four boxes, we call this the sum. And since we multiplied, product is a fancy math word for multiplying, we call this the product. Okay, let's try it one more time. Same thing over here. I've got two different algebraic expressions. I'm going to let one represent the height, so I'll put the 5k minus 3 over here on the side, and then I'll take the 2k minus 1 and put that across the top. And then I'm going to go multiply, right? 5 times 2 is 10. K times k is k squared. And then I multiply, so I've got negative 5k. and then negative 3 times 2k is negative 6k, and then negative 3 times negative 1 is a positive 3. And then I add my 4 boxes together, so I'm going to get 10k squared minus 5k minus 6k plus 3. Right? All I did there was I just added my 4 boxes together. Then I'm going to combine like terms, right? So I would have 10k squared, and when I combine negative 5 and negative 6, I get a negative 11k plus 3. So that's my equivalent expression that I'm looking for. 10k squared minus 11k plus 3. This is the product. This is the sum. They both represent the area of this big rectangle, so they are equal. Okay, they are equivalent to each other. All right. Now, notice in these ones, right, they didn't give us the factored form. They didn't give us the product. So we are going backwards here. So we are going to go backwards from what we just did in those first 2 examples. Instead, they gave us the sum, right? So we're going from sum back to product, and this is when we use our factoring skills. Okay, so factoring is the exact opposite of multiplying. So it's the opposite of what we did up above. All right, so to go from sum to product, I'm going to take my sum, I'm going to fill in my boxes because that's where they came from, right? The x squared would be up here in the upper left. This minus 4 would be down here in the bottom right, and this negative 3 came from combining some like terms there at the end, right? So I don't really know how this negative 3 came to be, but I do know that these 2 boxes that I don't have filled in added to give me that negative 3x. I'm going to put that in the bottom of my diamond. And then to finish my diamond here, I'm going to multiply this diagonal. So I get negative 4x squared. So I'm looking for 2 numbers that multiply to negative 4 and add to give me a negative 3. Okay, so that's going to be negative 4x and positive 1x. Okay, so if I multiply those, I get negative 4x squared. If I add these, I get negative 3x. So that's the combination that I'm looking for. Then we go around the outside and we find our height and our width. Okay, so we need x times x here to get the x squared, and then x times negative 4 gives us the negative 4x, and x times 1 gives us the 1x. And now I can see my width, I can see my height, and I'm going to fill those in. Right? So we have x minus 4 times x plus 1. That expression is equivalent to this expression. They both represent the area of this big rectangle. Okay. We'll do it one more time here. For this one over here, again, they gave us the sum, and we have to go back to the product. There we go. So I'm going to start the same way. I know the x squared has to go here in the upper left. The 6 has to go in the bottom right. I'm going to set up a diamond. That 5x, that's going to be these 2 boxes. They have to add to give me 5x, so it goes in the bottom. And then they would also have to multiply to give me 6x squared, right? Because I multiply that first diagonal. The diagonals have to multiply to give you the same thing. Okay, so I'm looking for 2 numbers that multiply to 6, but add to give me a 5. So that's going to be 3x and 2x, right? 3 times 2 is 6. 3 plus 2 is 5. So that works. And then I can start working on my outside dimensions, right? So for the x squared, I know I need an x and an x, and then I know x times 3 gives me 3x, and then x times 2 gives me 2x. So my product is going to be x plus 3 and x plus 2. And now I have 2 equivalent expressions. And this is going to come in handy when I give you 2 expressions and I ask you, are they equivalent? You can show me they're equivalent just by factoring, or just by multiplying like we did up above. Okay, so these skills are absolutely vital in rewriting some of these expressions. All right, so let's take a look at some more complicated models that might be, I don't know, a little bit more to think about here. So just remember that these are in fact rectangles, right? And they want us to write a sum and a product here, so we'll do that. But first I want to focus in on this rectangle, and I want to fill in all of the blanks that I possibly can. Okay, so for instance, since I know this is a rectangle, I know that opposite sides have to be the same, right? So if this is a 3, this is going to be a 3 down here. Okay, and if this is an x, this is going to be an x up here. right? And then I know that the area in here is x times y, right? So then that would have to be width times height. So this would have to be y, right? Because x times y is xy. Well, then now I get the middle box, right? So 3 times y would give me 3y. And then over here, if this is y, this has to be y. Right? And since this is y squared, it would have to be y times y. Right? Y times y is y squared, which makes this y. Okay? So now if I'm thinking about the sum, remember the sum comes from adding these three areas together. Right? So we would say the sum is xy plus 3y plus y squared. And none of those are like terms, so I can't combine them at all, but this would be a way of representing the area of that entire box, right? I just added the three separate areas together. Now the product is found by taking height times width. Okay, so I got to get the height of the entire box, which is just y. And then the width would be the addition of these three things up here. So I'm going to put this in parentheses, right? Y times, and then the width is x plus 3 plus y. And there's my product. And as it would turn out, these two things are indeed equivalent. They are the same thing. They both represent the area of this box. All right, let's see if we can do this one too. So again, just remembering that this is a rectangle. If this is -3 over here, then I know that this has to be -3 over here. If this is -4y down here, this has to be a -4y up top. And let's see here. So we have a -15. So -3 times something that would go here would have to give me a -15. So that's got to be a 5. Okay, and then over here we got -3 times something gives me -6x. So that would have to be 2x, right? -3 times 2x gives me -6x. And I'm starting to fill in some stuff here. So I've got a 2x up here now and a 5 up here now. Okay, so let's see what we can do. So if I do -4y times -3, that would be a positive 12y. So we got one of our boxes. And then over here, we have to figure out what would go in this box right here. Well, let's think about this. I have a -20xy in this one. So -4 times 5 would get me the -20. And then I would need an x, right? Because y times x gives me xy. All right, so that means that this is 5x over here. And then I can multiply these two to get this box. So 5 times 2 is 10. X times x is x squared. And then we would do 5x times 5, which is 25x. And I think our box is now complete. Okay, so to get my sum, I'm going to add up my 6 boxes. So I'm going to take 10x squared minus 20xy plus 25x minus 6x plus 12y minus 15. Looks like a long expression, but it does represent the entire area. And we also have the possibility of combining some like terms, right? So 10x squared wouldn't combine with anything. The -20xy would not combine with anything, but the x's would combine. So we could say 10x squared minus 20xy. I'm going to combine these two, and that would be a positive 25 and a -6. So that would be plus 19x plus 12y minus 15. So there we go. Either one of those would be a good expression. All right, now the product, right, is going to be the overall height. So we'll say that is 5x minus 3, and I'll put that in parentheses. Okay, that's just this side right here, which is the combination of the 5x and the -3, right? I would add those together to get the total height. And then the total width would be the addition of these three things up here. Okay, so I'm going to create another parentheses for my width, and we get 2x minus 4y plus 5. So this is another way of representing that same area. All right, last one we're going to do. And we've got the product given to us already. Right, so there's my product. We want to write the sum and fill in our box down here. Okay, so let's say this product, right? So we're looking at this first parentheses. This is going to represent the width. So I'm going to say x squared, 3x, and 9. All right, so there's my 3 parts of that width represented in the area model. Now this 2x minus 1, this is going to represent our height. So over here on the side, I'm going to put 2x minus 1, just like that. And if you want to, you can come down here, right? So if x squared is up here, you can put an x squared down here. Same thing with the 3x, same thing with the 9, and then over here you can put that 2x minus 1. That way you have every height and width that exists in this rectangle. And then we're going to go through and we're going to multiply. All right, so 2x times x squared is 2x cubed. 2x times 3x is 6x squared. All right, don't forget to multiply the x's. X times x is x squared. All right, then we're going to come over here. We'll do 2x times 9. That's 18x. And then down here, we'll do negative 1 times x squared, which is negative x squared. And then we'll do 3x times negative 1, so that's going to be negative 3x. And then over here, 9 times negative 1 is negative 9. So to get our sum, all we have to do is add those 6 boxes together. Okay, so just write it out. 2x cubed plus 6x squared plus 18x minus x squared minus 3x minus 9. And then we just got to go through and combine like terms. Okay, so I'm going to switch colors here because I just want to underline the things that are like terms. So like when we say like terms, anything that has the same variable raised to the same power is a like term. So for instance, this has an x that's being raised to the third power. So I go and I check the other things and I'm looking for an x that's been raised to the third power and I don't see one. So this doesn't have any other like terms that can be combined with. Now this one has an x to the second power, which I have one of those right here. So these two can be combined. Okay, and then I'm going to grab a different color and I'm looking at 18x. So it's just an x, not being raised to anything but 1, right? So 18x would combine with this one here because it is also just an x, right? So these two would combine. Okay, so I'm going to write it out. So we're going to say 2x cubed, and remember 6x and negative x squared both combined, so we're going to get plus 5x squared. And then the 18x and the negative 3x are going to combine, so that'll be plus 15x, and then minus 9. And there's my final sum. So this will be 2x to the third plus 5x squared plus 15x minus 9. And these two expressions would be equivalent. Alright guys, that's it for today. I probably overloaded you a bit. Don't worry because we're going to do some more tomorrow, so you'll see some more examples and have opportunities to ask questions. Alright guys, have a great day. See you later.